Thank you, Chris. What a wonderful introduction. I'm a big fan of your work as well. So I'm going to talk about control. This is something that my group and me have been working about in the last 2-3 years. My name is Elad Hazan, as Chris said. And these are people that the work we've collaborated with and the work is based upon. Some of them are my students. Some of them, Max Simchovich is a student from Berkeley, and Sham is a professor at UW. The main collaborators in this work that I will present today are Karan Singh, he's a student of mine. Cyril, also a student of mine, I don't know if he's here. And Naman Agrawal, who is a full-time member at Google Princeton. Before I kind of dive into the theory, I'll just say that we have implementations of the algorithms I will describe. They are on this GitHub, which is owned by John Hallman, and they're implemented by him and Paula and Alex, who are all undergrads in Princeton. So this talk is about controlling dynamical systems. It's a form of reinforcement learning which is continuous. So we have inputs which are denoted by U. Took me a while, 2-3 talks before I kind of got the notation right. So inputs are U, then outputs are Y, then we have a hidden state, hidden or not hidden, depends on the setting. It's called X, and this evolves according to some dynamics. And there are several problems that are studied in this context. One of them is prediction. For example, we can see all the input and past input, past outputs. We want to predict the next one. Or we want to do control. That's a more interesting and more complicated version, which says you want to input some U's and to achieve some functionality from the outputs. So you can think of an example. People use this hidden Markov models, right? So you have, they used it, for example, for a translation. You have inputs which are vectors from a language, then code some words in English, and outputs in French. That's prediction. That's not control. Control models a host of problems in usually continuous problems in motor functions and so on. Tracking. So I'll give some examples as we go along. But this is the mathematical model that we are concerned with. And for the most of the talk, I think of dynamics as being linear. So this can capture pretty much everything so far. But usually I think about linear dynamics. So X, the state evolves according to some linear transformation A. And the input also is applied on some hidden linear transformation. And there is some noise W. Okay? I'm guessing many of you haven't seen this before, or at least I have never seen this more than 3 years ago. But now kind of I'm used to it. So it's a nice model, and we'll see ways to attack it using machine learning. So we submitted a paper to NeurIPS, and we got some reviewer. I'm actually a big fan of deep learning, but this person was probably from the control community. So he said, as opposed to deep learning, control got us to the moon. That was one of the statements. He meant it in a positive way. I was very happy to hear. But basically, control has been around forever. It did get us to the moon. There are a lot of interesting algorithms and methods that were developed in the 60s, and you all heard about the Kalman filter. But many things have changed. And the field only recently has been picking up. So, for example, right nowadays we have deep neural nets, recurrent neural nets, LSTMs, and so on that are used for control, used for reinforcement learning, and these are not completely non-existent in the theory of control. One thing which is very common in machine learning is misspecified models. So maybe we want to everything works, everything we said works for linear dynamics, but our dynamics is not nonlinear. Okay, so we can think of trying to model that by noise which is non-stochastic or adversarial noise, various shifts in the model, and so on. Oh, this is Paula who wrote the code, some of the code that I described before. So noise can be non-stochastic, Gaussian, and so on. We have high-dimensional data for which we want efficient algorithms. And by efficient, I mean, so it is common in the control literature to use sum of square relaxation, semi-definite programming relaxations. These are polynomial time algorithms, but they are not practical. They're not efficient. So if we have dimensions that scale with thousands, we definitely don't want to use any sum of square relaxation for that. Okay? Maybe theoretically it's nice, but it's not practical at all. So all of these are things that we want to address. And in this talk, I'll talk about, I don't think I'll get to all of it, but whatever we get to. So the main thing I want to talk about is non-stochastic control, how to model deviations from the linear model and perturbations that are adversarial. Then I'll relate this to the Kalman filter and how we can improve upon it. And probably I'll get to boosting. So this is what happens when we have like neural networks. They're very, we have to use, these are the state of the art in supervised learning. How can we use them for reinforcement learning with provable guarantees? Probably I will not get to spectral filtering, but that's another interesting topic. Okay, so first part, control with adversarial perturbations. By the way, feel free to interrupt me at any time and ask me questions about anything. We have an hour, but I know some people have to leave before, and it's not like I won't need to get through everything, so I don't mind. Okay, so let's consider linear dynamics. So we have this control problem, input u, output now the same as the state x. We can view it, suppose we can view it. And our dynamics is going to be linear. So the state is going to be manipulated by a linear operator. And also the control that we put in is also apply the linear transformation and add it to the state, the next state. Okay, so in classical control, so what do we want to do? We want to minimize some kind of cost or average of cost in the long run. Okay. Now, in classical control, these costs are usually quadratics. If you ever heard of the linear quadratic regulator, that's a very common control primitive used for various devices, cooling of data centers and so on. But you can think of more general loss functions. That is the focus of one of our focuses. And the other is that these perturbations are usually, that are added to the state, they're usually thought of as IID Gaussian. This is a very optimistic kind of model. And I want to think about the case where this is adversarial. So why do I want to think about that? First of all, if we can say something meaningful when these perturbations are adversarial, we have a much more robust system, right? We can handle non-IID and so on, much more robust kind of systems. Second of all, this is a way to model nonlinearity. Okay? So if we have a nonlinear system and the deviations are small, we can think of them as adversarial perturbations. Okay, so these are two important things that I want to attack. And the other important thing, but less, is a kind of adversarial loss functions that also can capture adversarial noise. Okay, any question about the model so far? So this is the regime of robust control. What has been done in robust control? There is the LQR. This is a very kind of well-known primitive in control. It handles exactly what I said, but when the perturbations, the noise is Gaussian IID, and the loss functions are quadratic. That's the setting. In this case, you can use something called the Riccati equation from differential equations. You can solve it completely. You can come up with a controller which is optimal. Okay, again, these are very strong assumptions, but also a beautiful result. So the optimal solution turns out to be linear. The control U that you will play is a linear function of the state. And this turns out to be optimal. Okay. So it has this form. And this is kind of maybe the most common primitive in control. The other thing people looked at, this is not common at all, is age infinity control. This is the attempt to kind of are there, by the way, people who are control theorists in the audience? I wonder. No? Wonderful. This makes my life easy. Oh, okay, only. So age infinity control, please correct me if I'm wrong. I'm in the classical literature. So age infinity control basically tries to tackle this issue of adversarial noise. But it's a very pessimistic model. What does it do? It says, okay, I'm trying to think what is going to be my worst possible noise ahead of time, and then design my system to the control for it. Now, the downside of this, of course, is that it may not be. You design for the worst case, then the worst case doesn't happen. Something much wonderful happens, then you are stuck with a bad solution. So it's a pessimistic form of solution. And this is the mathematical way to model it. Some other problems, there are many problems with age infinity control, which is why it's not used very often. First of all, pessimistic, but also it's computationally not well behaved. This can sometimes be computed for quadratic functions, but if the functions are even convex, but not quadratic, it's not known how to compute this efficiently.
So we are assuming that, is there an assumption about the functional form of how you control, or just use these on?
Yeah, they assume linear dynamics and Gaussian noise, yeah. So sorry, adversarial noise, but linear dynamics, A and B. So same as in this slide, right? So they assume this model, but they kind of say, what's the worst case bounded noise? Let's say all the W's are bounded by 1. What's the best U I can? This is a closed form kind of problem. You can compute what it is. Yeah.
Elad, you assume that A and B are known, right? You don't need to estimate them.
That is correct. For this part of the talk, yes. We know how to handle unknown things as well.
And just another question, because it's a first order dynamics. In any case, the optimal strategy would be the time t would depend on your next time t, right? Or not true.
No, not necessarily.
Because you sum up all the costs.
Yes, it's not necessarily true, yeah.
Okay,
It can depend,
method,
right. It depends. So there are all sorts of, I don't want to go too deep, but it depends on how stable is the system, does it decay over time, and so on. There are all these parameters here that I don't want to elaborate on, but it can depend on the past in general, yeah. Just like a policy in reinforcement learning can depend on, many things, yeah. Okay. So what's missing from these? These are the two main things in control. What's missing? Okay, we want general losses, not only quadratics. We want computational efficient algorithm, very important, obviously. And we want an optimistic metric that handles worst case noise, but not in a kind of super pessimistic way. So here is the model that we consider. Consider, some of you, those that are familiar with online learning will find this very natural. So I'm thinking of online learning in this setting. I'm making an online sequence of predictions. Every time I select a U, and I accrue a cost of CT. So far, so good. This is what control does as well. But my metric now is going to be different than what is classically considered in control. For me, it's supernatural, but for somehow this was missing. Okay. So what we want to compete is with policy regret. Policy regret means I compete with the best policy in a certain class. Best policy in hindsight from a certain class. This is what I want to do. This thing is well defined, even if the perturbations are adversarial. It's always well defined. Okay? Does not require. Furthermore, now the kind of big question is, okay, what kind of policies do you want to compete with? That makes sense. So for this talk, I'm going to restrict myself to something which is very simple, linear policies. So all matrices K that I choose U to be K times the state. Why do I choose that? Well, first of all, it's easy for me to explain. Second of all, this is pretty general. This captures what LQR does, right? So LQR exactly does, it's shown to be optimal in the noise stochastic IID setting. I should remark, we know how to extend this to dynamical kind of policies, certain class of restricted dynamical policies, such as the Kalman filter. But I'm not going to talk about this today. Okay? So that's what we want to achieve. Any question about what we want to achieve? Yeah?
I assume the W will be somehow bounded, right?
Yes, of course, of course. Thank you, Boaz, yeah. So definitely the W's are bounded. Otherwise, you can be doomed. Yeah, definitely. Good question. Yeah?
So you compute with time-dependent K, so I understand.
You can do that, yeah. For simplicity, let's not do it now, but it can be done, yeah.
If the costs are near quadratic, is it understood whether a linear policy is near optimal?
I think the answer is yes, that there are all these, you can basically do a Taylor approximation, right? And every function is quadratic up to some approximation. If it's near, you can kind of throw away the third order term, say something. I think you can do something like that. But nevertheless, if you're, for some very interesting loss functions that we use in machine learning a lot, let's say you have the hinge loss in SVM. It's very common, very useful. You cannot, it's not quadratic at all, right? And then you run into huge computational problems, classical approaches, not to mention the adversarial noise. Okay? Any other questions? Okay, so.
Just a quick question.
Yeah, Samori.
The form that you showed earlier, ut is equal to kxt.
Yeah.
Did I assume that W was a Gaussian, or?
It is, yes. So what the control people classically proved is that if the noise is IID Gaussian, that's the optimal policy, kxt. That is why this is what we compare against. We choose to compare against this policy class because it makes sense. We kind of say, okay, look, this is more general than LQR. If the world is indeed what Gaussian, IID, and so on, at least you get the LQR back. But of course, it's much more general. Okay? Okay, I should mention, this is important, okay? This is not standard regret that we compete against the k at every iteration. It's counterfactual. We want to say we're going to compete with the k that would have done the k from the beginning of time. Otherwise, it's kind of a silly metric. You want to be counterfactual. And the noise are bounded, like Boaz mentioned. Let's say by 1, doesn't matter. So this is the main result 1. We can get this a regret for this problem in this exact setting I mentioned, which scales like square root number of iterations. Okay? And the algorithm is going to be efficient. I'm going to describe it. Polynomial in system parameters and polylog in time. Okay, so all of this is pretty efficient. It's implemented in this GitHub thing that I pointed to, John Hallman and Paula and Alex, and you can, if you want, you're welcome to play around with it. Yeah?
The dimension doesn't show up anywhere?
System parameters means that the dimension includes there. So,
Sorry, in the regret bound, there's no, this is...
yeah, there is. So all of these terms appear here too, yeah. So, polynomial, for all the algorithms that I have ever worked with in my life, polynomial doesn't mean, to the power 20. No, it's like maybe power 1, 2, not more than that. And it's all dimension, kind of the natural things. Okay, so dimension of the matrices and so on. These appear here. Okay, yeah.
Just to unpack this because I'm new to the setting. So there's an efficient online algorithm that sees x, y's, and gives you the next ut to plug in order to minimize the cost so that the regret guarantee is satisfied.
That is exactly correct. Okay, that's the main result 1 I'm going to talk about. Okay. Good. So if you all understand the result, like what it says, I'll tell you what the algorithm does. So here is what the algorithm does. The algorithm is a perturbation-based controller. It's kind of different from, it does not actually apply to the state. It competes with the k, but it doesn't do that at all. It doesn't work on the state at all. It doesn't care about the state, okay? So here is what it does. If you kind of think about the policy, about the optimal control with a k, it's going to be some polynomial function because you can unroll the dynamics and you have powers of the k. Okay? That's how it looks like. This, of course, is pretty terrible, right? If you want to find the optimal k here, this is a polynomial. There is no reason for this to be convex, and that's why this is hard. Nevertheless, we can relax it. Just call all of these matrices to be something else, M, okay? Call it M and use that. I'm going to learn this M. So it's a reparameterization, and I'm going to use a perturbation-based policy. So my control is going to be a linear function of all the previous perturbations. Okay? That's how the control is built. Of course, I need to tell you how to learn these M's and also why does it work. And how do I know the perturbations? So the third thing is easy. If I know the system and I know the state, I can recover the perturbation. If I don't know the system, I need to do something else, which I'll maybe allude to. But otherwise, this is a well-defined controller, right? So one good thing to notice is that now the best policy in hindsight, at least, is easy to compute. At least that's convex, right? I can now compute it. I just have a linear, my control is a linear function of the perturbations and the policy. Furthermore, one very important point here is that I kind of got rid of the counterfactuality. Because I'm working with perturbations, how was the whole system generated? Some adversary chose the perturbations in the system. The perturbations do not depend on what I'm doing. Okay, they're fixed. So therefore, I kind of got rid of the counterfactual issue here. This is an important point.
Elad?
Yeah.
Now, if you think of the perturbations as deviations from linearity,
Yeah.
is it
That is a good point. Yeah, I think that's in this particular model, I think they could. Yeah, you're right. So if you think of this, that's true. In this particular case, the counterfactuality is not preserved. Yeah, that's true. Good point.
Reminds me of the adder graph, similar issue. The competitive ratio doesn't capture, and the regret doesn't capture what actually happened.
Yeah, it doesn't capture everything. So it captures some things. Like if I were to say that it certainly captures some perturbations, but not adversariality, but not everything. There is a stronger notion of adversariality, which is adaptive adversariality, meaning that you can choose W based on what you have done. This technique actually works even under that, and it will capture what you mentioned. But so I guess maybe that's a better answer to you. So I allow you the perturbation to be based on your actions. But then this is kind of a more delicate. So this kind of a more delicate. I don't want to go into it. Think of perturbation chosen ahead of time. But excellent point actually. Any other questions? Okay. Those of you with background from control, with no background from control, you might think of K to be 0 for this slide. If you have background in control, there is something that you can compute ahead of time. If you know the system, there's something called a stabilizing controller. This means it's not the optimal controller. It just means that it kind of takes the cost down to 0. And you kind of can assume that you have it in advance. Okay? Otherwise, you can think of K as being 0. And now, so our policy is a linear function of the past perturbations. We can add something with the state. Again, this is an extra. It's a bonus, but you don't have to. Now what I need to say is that indeed we can minimize regret over these M's. And it's not a trivial thing, because you choose some M's, they depend on the past. In the next iteration, maybe I choose a different M's, right? So it's not clear how, and my choice affects it's not clear that kind of I can compete with the best in hindsight with simple gradient methods. Just because I'm not choosing the same matrices all the time. So at different time steps, I can have different matrices that multiply the same perturbation. Okay? So one thing that we need to prove is that if you have enough memory, then any stable policy can be emulated by such a controller. Something we need to prove. And the other thing to attack is this issue that at time t, there's a lot of notation here, but at time t I choose a lot of matrices that go back into the past. And these are not the same matrices I used in the last iteration, right? Last iteration I used something else to multiply the same perturbation. So this issue needs to be attacked. And indeed, there is a methodology for doing it. It's called online conflict optimization with memory. So basically, if we have a bounded memory, which we have because we have assumed that we have a stabilizing controller, so things decay over time, then indeed you can minimize regret proportional to square root number of iterations and the length of the memory. So this is another component that we use pretty much as a black box. So here is how the algorithm looks like. You start with some arbitrary matrices and a stabilizing controller K. What you do is you observe the state, you estimate the perturbation, because you know the system. You construct the counterfactual loss, which is a function of the matrices only, and you update using a gradient methods on these functions, and use that as your control. Yeah, question? What is smaller than 0? Can you repeat?
T minus I, so the double
T minus I?
So if you sum I...
Okay. 0. Yeah, make it 0. That's fine. Yeah, make it 0. It's another constant Q to the regret. Yeah, it's fine. This is the algorithm, and it achieves the regret bound that I alluded to before. And again, you have to go through these steps. Yeah, so that's result number 1. Okay, and it achieves everything that I said. This, again, it's a different kind of algorithm than previously used in control. It's an adaptive gradient method applied not to the linear policy, but to something else, to reparametrization. Yeah, question, Sushan?
So So once you update the M, you go back and you repeat it at the same step, or is this the set of M that you feed to the next set of inputs?
I keep on using the new M's. It's not like I use the previous. I keep on updating all the M's every iteration.
So every time step, there's just a single update to the matrices, which then gets
Yes.
fed to the next.
Correct. And even though you don't use the same M for the same noise, it's still okay. And this exploits the Lipschitzness of the function. So you can say, okay, because it's slowly moving, I'm using a very slow learning rate. It doesn't matter that I didn't use exactly the same M. That's kind of how the analysis works, and everything gets to be root regret, which is the same as LQR. So the regret bound we get actually is the same as LQR, but of course in a much more general setting that you have adversarial analysis, you can have any loss function. Convex. Yeah.
Why in step 2 you say estimate WT plus 1, right?
Compute. It's not because Karan wrote this slide, so I copied this
No,
slide
but it's
from him.
also not the exact perturbation, right? Because you don't have the exact.
No, it is the exact.
It is the exact. You have A and B, you have everything. You have X, you have A, and you have B, and you have the U that you played. Okay? It's exact.
And you need to choose eta somehow.
Right, so eta is chosen to be roughly 1 over root number of iterations. That's classical online learning. Okay, any questions about this part? How am I doing with time? Okay. So a kind of a consequence of this method is that actually we can improve upon some well-known constructs in control theory even in their own game. So if I assume the same kind of model, but this W is now Gaussian. So thus far it was adversarial, okay? But now just kind of indulge me, okay? I'm going to assume that it's Gaussian. In this case, we can do something even better than classical control. So suppose that my cost functions are quadratic. This is called the tracking problem. There is some object, the moon or whatever, that I want to track it, and I'm going to choose an X. This is only prediction, okay? I'm choosing an X to kind of see how close I am to it, and it evolves linearly and so on. These kind of cost functions are strongly convex in the in the original parameterization of the problem in X, which is nice, but they are not strongly convex in our reparameterization, okay? Because now we have some functions over the M's. They didn't exist before. Nevertheless, here's the result we can get. We can get some kind of controller that produces these U's and has polylog regret. So that's called in statistics fast rate, I think. Boaz, correct me if I think it's what they call it. So it's like a fast rate for the same problem that classical control people had, even though, right? So that didn't exist for that particular problem, strangely enough, okay? So how is this done? I'm just going to kind of briefly say, so the previous reduction I described has functions that depend on, I kind of reparameterize X and the U by M, right? Going over all the past perturbations. Now, even though I have a quadratic in U and in M, it doesn't mean that as a function of the matrices, it's strongly convex. It doesn't mean that, because I have over-parameterization, right? So it's not immediately clear. In fact, in order to make the system stable, I need log T more parameters than before. Okay, nevertheless, it is possible to say that if the noises are Gaussian, if these things are Gaussian, basically when you square them, you have the variance in them, they behave nicely, and the whole thing becomes convex in the M's, strongly convex in the M's, and therefore you can get, using just online gradient descent or some modifications of it, you can get logarithmic regret. All right. Any question? So this is useful even for classical tracking, even if you don't believe me about the worst case model. Now, what if we don't know the system? So it's possible to get T to the 2/3 regret, even if you don't. There's some recent work with Sham and Karan and Max Imchovich, the visiting student. We can even get root T regret for the LQR problem without knowing the system. So this is really a strict improvement. If you want, it's some kind of improper LQR. So you don't know the system at all, and you play a control which is not an LQR, it's something else completely, and yet it gets the LQR rate of root T. So I think that's pretty surprising. Yeah?
For the classical LQR solution, you can get analytically from a Riccati equation.
Correct.
Can you reverse engineer an equivalent differential equation for which the analytic solution is your algorithm?
That's a great question. I don't know. I mean, I never think in this way. In my opinion, it's a convoluted way of thinking to do this, but it's a good question. I don't know. Yeah. It's very interesting, by the way. Yeah, I think it's a very interesting question. All right. So next thing I want to talk about is what to do when you have deep controllers. So that was like one kind of relaxation, right? We have adversarial noise and so on. Now I want to say, okay, the world has changed since the 60s. We have these deep nets and LSTMs and whatnot. So Chris is an expert on these things, right? We want now to combine them to do control. Yeah, this joint work with Naman and Natalie and Zu. So here is something rigorous you can say, even though you have deep or some other deep controllers. And this is a theory of kind of boosting for these creatures. Again, we're working in these dynamical systems that change with perturbation. We want to minimize costs. And our goal is to minimize regret. So same setting exactly as before. Okay, so we want to minimize policy regret. And I want to take some controller for which I assume something about and improve its performance. That is the goal of this part of the talk. Because I cannot go into, before I could kind of go into and say something rigorous. I had a linear system. Now it's a non-linear system. It's a weird deep net. I don't know anything about it. How can I formalize it and improve it? That's the question I want to ask now. So the background is online boosting. So online boosting has been considered for regression. It's not even clear what it means to do boosting in the online setting. Not to mention control. Control, we have the state, even more problematic. Yeah, Chris?
Is policy regret to some linear controller? Is that right? Or no?
No. It's no. This is going to be some class, yeah. So linear doesn't make sense here because anyways you have these deep nets. What we're going to do is get a guarantee kind of looking forward to a larger class than the originally. Maybe someone gave you a family of nets. I want to enlarge this class, kind of do better than that class. Okay. So, So this is kind of a prelude. This is the technique we're going to use. So boosting has been considered, I hope all of you know boosting for classification. It can be defined for regression, okay? But it can also be defined online. Online is important. What does it mean to do boosting online? You don't have a distribution. Classical boosting, you have a distribution. You assume you can get half minus epsilon. You want to boost it to 0 error, right? What does it mean for regression? So here is a meaning that I think is a good one, okay? Basically, you assume you have an online learner. That's an algorithm that can minimize loss with respect to some family of predictors. So every time you get an example X, label Y, and you can manipulate it by some F to generate a prediction and see the aggregated loss, and you can minimize regret with respect to this family. That's the assumption. You have a regret minimizing with respect to a simple strategy. How can you boost it? So you can combine these weak learners by every time applying the weak learner to the residual loss of the previous algorithm. That's the method. So basically, you have the predictor of the first weak learner, and you kind of give it as the residual loss for that to the second weak learner, and so on. So you do that every iteration. You go through all the weak learners, move to the next iteration. Go through all the algorithms, go to the next iteration, so on. Why is it good? So here is the regret that you can obtain. What you can guarantee, you have already regret bound. That's kind of, you cannot hope to improve the regret. But what you can improve is the class of predictors. So that is what alludes to what Chris asked. Suppose I'm competitive against all perceptrons. What I'm able to compete now against is the class of all convex Hall of perceptrons, or maybe a depth 2 kind of neural net. That is the strength of this result. So it takes weak learners to compete to one class and can improve it to compete with a bigger class. Okay. I want to use this for control, but for control, there is a problem, right? I have these states here. So every weak learner has a state. I can't just take them and kind of take the residual of one, convert to the other. The first person has one state, the second has a different state, and so on. So it doesn't make sense to do it. Okay. So so the question is, how can we combine these weak predictors into one with state? So I'm going to describe how to do that. So what I'm going to assume is that my dynamical system is stable. This is pretty much used. I don't know to say anything at all about systems that are not stable. So it's not a difficult assumption, okay? So systems are stable. This means they have a finite memory of history, okay? And what I'm going to do in this case is now, Okay, so under this assumption that the distance passed is negligible, I can reduce each weak learner to a weak learner over loss functions with history. Yeah, Sanjeev?
So that the memory is finite, I mean, it should depend on the dimension.
Yeah, definitely.
So it's allowed to depend on the dimension.
It's allowed to depend on, and you, in fact, don't even need to know on how much history. I mean, you'll get a guarantee that depends on the history, but you don't need to know in advance how much history there is.
So that history could depend on the
Yeah. It can even, the history can even be growing. You just need to grow kind of sublinearly with time. Yeah. So once you kind of reduce the loss function, kind of assume the system is stable, I can construct loss functions, just like I did in the previous part of the talk, that have a lot of history in them, and now basically they don't have memory anymore. They just have a lot of history. Okay? And now I can use online gradient boosting. So, okay, so my assumption is again some weak learning assumption that I can minimize regret with respect to some class of policies or predictors. And what I'm going to apply online gradient boosting to these modified loss functions that take the history into account. So the way to do it is to give each weak learner a loss function which depends on what the previous weak learner did. So formally, I'm taking the gradient of what the previous person did, and a linear function multiplying that by the new parameter, and that's the loss function I give to the next learner. And I applied it sequentially. Okay? And all of this, of course, upon these loss functions with memory. So it's not applied immediately to the current loss function. You have to kind of go back in time. So this is the technique. This kind of an illustration. You basically have two arrows. In one hand, you go forward with every iteration. You, from scratch, feed the prediction to the first one. It's residual to the second one, residual to the third one, and so on. And combine all of these uniformly, and that's your prediction. Okay. Okay, this is kind of pseudocode. I'm not going to allow, I don't think we can, doesn't help to look at it. But here is the regret bound. So given weak learners with certain regret, and this is for a control setting now with finite memory, you can have a state in there. Okay, it's not like just prediction. It can have a state. Then you can, this algorithm whose pseudocode I had in the previous slide, output a sequence of controls that have regret favorable to a convex hull of the family of policies that you wanted to begin with. Okay, so each one individually guarantees something compared to some kind of a policy class. I can now compete with a larger class. And the price that I'm paying is this one. So it doesn't come for free. I have the same regret bound, but plus a term that depends on the number of weak learners I take and on the history and so on. I don't need to know the history ahead of time. Okay. Any question about this? Yeah.
So there's a black box that there's like a deep net optimizer.
There's a black box. This is a.
You're going to use that.
How do I use it?
You are going to use that.
I am using it. So the algorithm, what it does, so basically each of these machines, AI, is a deep net. And every iteration, I'm feeding it a loss function and getting a prediction. This loss function depends on the residual loss from the previous neural net. So I'm kind of taking a bunch of neural nets and each one of them feeding the residual loss to the next one. And I'm taking the aggregate prediction of all of them as my final prediction.
You're not training them, they're pre-trained.
They could train as they go along. Each one of them is a learner. So each one of them is an algorithm by itself. It can do online. It's like think of a recurrent neural net or something like that. It could be pre-trained, could be anything.
But you're going to only take the residual, not propagate through.
It could be. If it's an online learner, it could. It whatever machine you have. I'm just assuming this machine has some performance bound. It could be a self-modifying machine that kind of trains as it go along.
You don't use that.
No.
It doesn't grow.
Not used at all. Yeah. Okay.
The regret, I mean, I guess I was thinking in terms of boosting where over time I don't want RFT in there, right?
Well, yeah, so in regret, you're right. Usually we look at like the average regret. So regret over t goes to 0, right? Is that what you're referring to? So this, okay. So this RFT, think of root t or something like that. That's usually how it behaves. And then if I scale by t, this is also some constant that goes to 0 with n, the number of weak learners. And this, all of this goes to 0. Okay.
But all I'm getting at is that in usual boosting, I sort of want my whatever the rate of my boosted algorithm, I want it to be much smaller than the rate of the weak learners.
That's right. In classical boosting, you want to do that. And you can indeed achieve it, right, in statistical boosting. In online boosting, we don't know such a theorem. All we can prove is that you have a regret bound. It's already regret, already goes to 0. You know, what can you do? What you can do is you can compete with a bigger class of machines. So here, this is the same regret as before. This didn't improve. What improved is the comparator class. Like instead of competing with a single f, you compete with a convex hull of many f's. Which is, if it's a nonlinear family, like a neural net, this is strictly more powerful. Okay?
However, we don't necessarily know that the best possible rates for the convex hull
is this? No, we don't know. Yeah. Nevertheless, so there are many things here that are tight. So first of all, you can imagine this RT that you can get without the convex hull. So probably you cannot do better for even a larger class, right? So this is probably tight. This thing is also tight in general. Like for the boosting methodology. Maybe you can do something else, but for boosting, this is tight. If you kind of don't look inside the machine, this additional term is tight. Yeah. Okay. Now, I do want to say something. So deep nets are wonderful, right? For supervised learning, they can learn whatever we know how to learn. The good thing about them is that if your net didn't learn exactly, didn't reach 0 error, okay, you over-parameterize, right? You take a larger net. And you have infinite data usually for supervised. You have a lot of data. Take huge data, take huge net, it will go to 0. This is not true for online time series prediction, right? So for online time series prediction, it doesn't help you to just enlarge the net. You don't have enough data. You have now made 50 iterations. It's not going to help you now that you increase the net, right? So actually, this is important. This is a distinction between online prediction and supervised learning. Okay, this is some experiments that Natalie and Zhu conducted. And this is just kind of a sanity check. This is actually an LQR so it's a linear quadratic. So we have a linear system with Gaussian noise. And then the optimum is given by the Riccati equation. And this is the purple line here. You cannot improve upon it. We don't improve upon it. It's optimal. Nevertheless, you can take the weak learner, which is the red line here. That's the weak learner I described, the perturbation-based controller. And now this is what happens when you boost it. So it improves. So this kind of just shows you that it improves. And the improvement is always visible for every number of weak learners that you take. It's kind of monotone improvement, which is a nice property. And of course, you can look at nonlinear noises. So if your noise follows a random Gaussian walk, now the LQR is no longer optimal, far from it. And you can boost, you can improve. And if you have some sine noise or whatever, some cyclic noise, obviously the same thing happens. So your LQR is very bad, actually. But the kind of the weak learner I described before is good and can be even improved more by boosting. Yeah?
So if I understand correctly, your algorithm is generating an ensemble of the weak learners in order to...
Correct.
So is the size of the ensemble growing exactly as the number of steps?
No. It's a fixed.
It's a fixed ensemble.
It's a fixed.
What's the size of the ensemble in the
You have to ask Natalie, but it's some maybe 10 or something. I know she's not here. Natalie is here? No.
Okay.
Yeah.
Small fixed.
some 10. You know, it works. If you do 3 or 4 already, you see a huge improvement. By the way, one of the lines here is RNN. This red line is a recurrent neural net, and this is how it's improved by boosting. Yeah, this again. So here is there's some more experience with control. It's actually a nice video. If you want to see, it's a good break in the middle of the talk. Can I run it? Oh, no. Yes. Okay. So. Well, you can see visible improvements even for controls of simple tasks like inverted pendulum and so on. Okay, there's some more experience with time series. How are we doing on time? Are we almost done, Sanjeev? What's the deadline here?
We have 20 minutes until
Yeah,
our
we
deadline.
have the room, but there might be questions.
Yeah.
And I myself will have to leave in a couple minutes.
So, okay, how about I'll do this? I'll just tell you something about something very, very small, then I'll leave like 10 minutes for questions, 10, 15 minutes for questions, okay? So I'm just going to say something. I'll take your question in a minute, if you don't mind. So, yeah, so one more thing that we worked on with Karan and Cyril, and this is a very beautiful basis that they discovered, that basically allows to do control even without knowing the system and not knowing the state even. Don't even know the state, don't know anything, okay? You can still do control in this setting. So this goes into, I'll just kind of very briefly say what it is. If you have a linear dynamical system that we talked about forever now, okay, and we want to do online learning. So here is the nice thing that happens. When you unroll the dynamics into the past, you have a polynomial series of matrices. You have this a to the I. And it turns out that this a to the I has a very beautiful basis. You can represent it very efficiently. Okay, so the spectrum of this basis decays exponentially fast. It's not a basis for all matrices. Only for matrices that are symmetric and have eigenvalue between 0 and 1, you can do it. You can extend it, but nevertheless, for this kind of matrices, you can write such a basis. And this is a very wonderful basis, so you can write some parameterization. You can pre-filter your controls. You can compute this filter ahead of time, nothing to do with the data, and apply linear regression on the filtered controls, and use that as your next control. And that will work with very few parameters that exponentially decay with the error guarantee. So that's kind of a nice construct. I think I'm not going to go into it. I'll take your questions. But if you have questions about that, I'm happy to answer as well. So maybe at this point, I'll just kind of stop here and take your questions and then continue from there. Thank you.